Hello, my name is Hasan, and today I'll be showing you how to calculate the ideal gas law constant experimentally. There are a few things I would like to explain to you before we begin the lab experiment. And first of all, we're going to be using hydrochloric acid in a highly concentrated solution, so it's very important that you use your goggles and gloves. It's important that you take your time with this lab, because rushing through this experiment can cause you to make careless errors, and those can cause you to have to repeat a trial. And trust me, if you take your time, you'll still get out with plenty of time left. You'll get out much sooner than you will with your other labs, so you have plenty of time to study for chemistry. The first step that we need to take is to measure 0.14 grams to 0.16 grams of magnesium. And it's important that we measure within this range because using too much magnesium can cause too much hydrogen gas to be produced. Using too little magnesium can cause too little hydrogen gas to be produced. And it's not really that bad if you use too little magnesium, because you can still accurately do your experiment, but you have to measure greater correction value for your pressure. But you definitely shouldn't use more magnesium, because that will overfill the graduated cylinder that you're using to measure the hydrogen gas's volume. Okay, so we got about 0.14 grams of magnesium, and we're going to put that in this test tube right here. It's important that you record the amount of magnesium that you're using, because you're gonna use this value to stoichiometrically calculate the number of moles of hydrogen gas that should be produced in your experiment. We got this new black neoprene stopper over here, and we're gonna make sure we put it on the test tube very tightly. And the reason why we want it to be on there very tightly is because when you add the hydrochloric acid with the syringe later on, the pressure in here is going to become so great that the popper could potentially pop off, and if that happens, you're going to have to repeat your trial all over again. Before we proceed to the next step, you want to make sure that you have a ring stand and a clamp set up just like this. For this next step, what we're going to want to do is get a container like this and a 250 milliliter graduated cylinder to be filled with water. So let's go over to the sink, and we're going to fill up this container about halfway with water. And that should just be good enough. I'm going to put that right under the clamp. And we're going to get this 250 milliliter graduated cylinder and fill it up all the way to the 250 milliliter line. And we fill it up all the way because when we invert the graduated cylinder for this experiment, water will probably be lost to the container. So what we want to do when we invert it, put your hand on top of it, and we're going to do that really slowly, and then put your hand underneath, submerge your hand under the water, and then release the graduated cylinder. This is just to make sure you don't have to hold it the whole time. If you want to hold it the whole time, then you don't even need the ring stand and the clamp. Now, the reason we want the graduated cylinder to be filled as much as we can is because when the hydrogen gas goes up the graduated cylinder, it'll accumulate over here and push the water level down. And using too much magnesium can cause excess hydrogen gas to be produced, and it might overlap with the graduated cylinder and be lost to the surroundings. That's why we don't want to use too much magnesium. Make sure to record the initial volume of the water level in the graduated cylinder, because if you do not do that, you won't be able to accurately calculate the change in volume in the graduated cylinder. And the change in volume, minus 10 milliliters for the amount of hydrochloric acid you used, will be exactly equal to the amount of hydrogen gas produced in the reaction. Alright, for this next step, we'll want to raise the graduated cylinder as much as we can while keeping it still submerged in the water so that none of the water in the cylinder falls out. Raising the graduated cylinder higher up makes it easier to feed the hose connected to the black neoprene stopper in the connection to the test tube into the graduated cylinder. Make sure the hose is fed at least 2 inches into the graduated cylinder. Okay, that's well above 2 inches, and we need to make sure that the hose is pinned down to the bottom of the container so it doesn't slip out while we're doing our experiment. So we're going to lower it and have it pinned down right there, and then tighten this back up. We want to pin the hose at the bottom of the container because that ensures that the hose will stay in the graduated cylinder. If the hose ever slips out of the graduated cylinder, then you can lose hydrogen gas bubbles to the surroundings, and that'll make all your measurements inaccurate, so you'd have to repeat the trial over again. Now, we want to pin the hose down at the bottom of the container, but we don't want to squish the hose, because if you squish the hose, that could impede the gas flow from the reaction with magnesium and hydrochloric acid all the way down to the graduated cylinder. And if it can't get past the point where the graduated cylinder is pinned to the hose, then pressure can build up in this test tube and pop the stopper off, which would make you have to repeat the trial all over again. Before we proceed to the next step of the procedure, we're going to want to fill up a beaker about this size, 400 milliliter beaker, with water so we can prepare a water bath for the test tube. The reaction with magnesium and hydrochloric acid is very exothermic, so we're going to use this water bath to cool the test tube off while the reaction is taking place. So we're going to place it in there just like that. And then we're going to collect 10 milliliters of hydrochloric acid with this 12 milliliter syringe. And we have hydrochloric acid in here in a 3 molar solution. Alright, there's 10 milliliters of 3 molars of hydrochloric acid. And without depressing the plunger, make sure you hold the syringe right here. We're going to put the syringe in the second hole of the neoprene stopper that is connected to the test tube. Add hydrochloric acid very slowly to the magnesium turnings inside the test tube, drop by drop. And you can see the bubbles accumulating at the bottom of the test tube, and you can also see the hydrogen bubbles traveling down this test tube and up here into the graduated cylinder. And as you can see, if you used too much magnesium, then too much hydrogen gas would have been produced, and it would have overshot the graduated cylinder, and it would have been lost to the surroundings. And you can see the bubbles in the test tube, and that indicates that the reaction is taking place. And if it's bubbling really violently, then you want to stop adding HCl altogether and wait for the hydrogen gas to travel from the test tube along the hose to the graduated cylinder. And once you see that bubbles have stopped traveling, then you should start adding the hydrochloric acid again, because you are no longer in danger of popping the stopper off of the test tube. The reaction may be completed before all the hydrochloric acid is used, and that's because the magnesium turnings are purposefully used as a limiting reagent to calculate the amount of hydrogen gas produced. And it's important to note that you shouldn't have any solid left over after you have used up all your hydrochloric acid, because the hydrochloric acid you use is in excess. But if you still do have magnesium left at the bottom of the test tube, then something went wrong in your experiment and you will have to repeat your trial over again. And an important thing to note is that when you're done adding all the hydrochloric acid, you do not take the syringe out of the stopper, because that will essentially open your closed system, and that will affect all the values that you have measured thus far. Okay, now we're going to measure the final volume, and the water level is right there. So once you take that reading, that'll be your final volume, and the change in volume will be your final volume minus your initial volume, and that value minus 10 more milliliters for the amount of hydrochloric acid you added into the system will be the exact value for the hydrogen gas you produced. Well, we have no device to measure the hydrogen gas's pressure directly, but what we will use is the barometric pressure, whose value is provided by your TA, and we'll compare that with the pressure in here with the hydrogen gas by comparing the water levels of the container and the graduated cylinder. Since the hydrogen gas hasn't pushed the water level all the way down to match the water level in the container, you can tell that the pressure of the hydrogen gas is less than the barometric pressure. So to calculate the difference between the barometric pressure and the hydrogen gas's pressure, we have to use a ruler to calculate the difference in centimeters from the water level of the container and the water level of the graduated cylinder. So when your TA gives you the barometric pressure in torr, you'll need to subtract your measured difference for your pressure value, and that'll be subtracted from the barometric value because the hydrogen gas's pressure is less than the barometric pressure. If the water level of the graduated cylinder is depressed below the water level of the container, that means the hydrogen gas's pressure is greater than the barometric pressure, and in that case you'll need to add the measured difference that you got from the ruler to the barometric pressure once you have converted the centimeters into torr. To illustrate the significance of the syringe staying in place of the test tube, I'm going to remove it, and we're going to observe the change in the water level of the graduated cylinder as we open the closed system. As you can see, the water level is slowly going down. Another important thing I forgot to mention is that we're going to use this thermometer to measure the temperature of this water in the water of the container, and this will be your value for temperature in your Pivner equation once you convert it from Celsius to Kelvin. Your lab journal should look somewhat like this, and as a quick recap, we'll walk through everything that we should have paid attention to in this lab. The mass of magnesium turnings will be labeled right here in grams, and we're going to use stoichiometry to convert that into moles of hydrogen gas, and that'll be used for the N value in your Pivner equation. And the volume of hydrogen gas produced is exactly equal to the final volume measured minus the initial volume measured minus 10 milliliters you added for the hydrochloric acid you used to put into the system for the reaction. And this is going to be in milliliters. And what you want to do is you want to convert this into liters before you use it in your Pivner equation. And the temperature of the system will be exactly equal to the temperature of the water in the container, and this will be in degrees Celsius. And you must convert this into Kelvin before using it in your Pivner equation. The pressure of your system is going to be exactly equal to the barometric pressure plus or minus the pressure correction depending on the water level that you observed in the graduated cylinder. And this value will be converted from centimeters to torr using this conversion factor. And then after that is subtracted or added to the barometric pressure, this will be your value for pressure in your Pivner equation. This will be in torr, so before you do that, you're going to change it into atmospheres. And then once you have gotten all your values, you're going to rearrange your Pivner equation to solve for R, and then you'll plug in all your numbers, and you'll get your ideal gas law constant experimental value.